Okay, so we're going to continue and, in fact, finish the derivation of how paramagnetism works today. At the end of the last lecture, we'd gotten up to finding the, the temperature as a function of energy. So, after taking account of the negative sign, switching the numerator and denominator inside the logarithm to get rid of the overall negative sign. There. That's what we came up with. And remember that these, what I'm calling sort of anti-symmetrical terms here, they're the same except for an internal negative sign there. These were from, originally it was n minus n up, all divided by n down. And we were able to use the equation for the total energy and total magnetization of the system to rewrite n up and n down in terms of these here. So n minus n up all over n up. Okay. Substituting in the things that we actually measure in u and then u and v, we found this and made it this nice anti-symmetrical form. Okay, that's going to become important in just a little bit. So our next step, remember, we're going through these 5 steps on how we find energy, heat capacity, these kinds of things. So now we're up to step 4. Given temperature as a function of energy, solve for energy as a function of temperature. Well, what are we going to do? We've got temperature on the left, I know 1 over T, but still. On the right, we've got the natural logarithm of something involving energy. Okay, so we're going to have to exponentiate. So the first thing we want to do is get the logarithm all by itself. So we divide both sides, or multiply both sides by 2 mu b over k. Notice now that we've got a kT term right there, which of course has units of energy. kT shows up all over the place inside thermodynamics. Now we have the natural log by itself, so when we exponentiate, the right-hand side is very clean. The exponential of the natural log of something is the something. So the left-hand side becomes e to the 2 mu b over kt. Okay. Now, I'm wanting to solve for the energy. The thing is, I've got it in 2 places here. Basic thing would be, I should cross-multiply. Multiply both sides. What about cross-multiply? I'll multiply both sides by this denominator here. That'll give me 2 terms on the left, but one of those will have energy in it, and on the right, 2 terms, one of which has energy in it. Let's see. All right, you know what? I'm not going to rewrite e to the 2 mu b over kt each time. I'm just going to write e to the little squiggly line means all the stuff that's in there. I'm not changing inside the exponential. Okay, now I want to gather the terms together that have energy in them and put everything else on the right-hand side. All right, so if I have u over mu b times e to the stuff, then plus u over mu b times, well, 1, I can gather those together on the left, and that'll be, let's see here. And these will go on the right, so I'll have m minus, I think I should gather the terms there. Okay. Well, let me rewrite this. I'm going to change the order on the left-hand side. So I've got 1 plus e to the exponent. All right. I had an e to the exponent plus 1. This way, you can see the similarity. Again, that same anti-symmetry that's gone on before. Well, what I want to solve for is just u. So, I will take, let's see, divide both sides by 1 plus the exponent, exponential, and mu b. Okay. That was right. Now, let me expand what was in that exponential. And let's see. So n mu b times 1 minus e to the 2 mu b over kt divided by 1 plus e to the 2 mu b over kt. Yes. Now take a look here. We've got 1 minus an exponential divided by 1 plus the same exponential. So there are what are called the Euler relations, E-U-L-E-R, and in geometry, where our trigonometric functions have equivalent forms that are exponentials. For example, you've got sine and cosine. You have, actually off the top of my head, I don't remember them, but you have, oh yeah, sine of theta is I over 2, I being the imaginary number, times e to the I theta minus e to the minus I theta. Cosine is 1/2 times e to the I theta plus e to the minus I theta. And then you take the tangent is just sine divided by cosine, and you get this ratio with difference of exponentials in the numerator, a sum of exponentials in the denominator. Well, we don't have any imaginary number in this exponent. But you do get what are called the hyperbolic trig functions, which don't have an I in the exponent, but otherwise they've got the same form. Okay, so let me see, I've got to move the camera over a bit. See if I've got any longer chalk. Slightly. Okay, hyperbolic sine, S-I-N-H for hyperbolic, usually pronounced sinh. is equal to, so sinh theta is 1/2 e to the theta minus e to the minus theta. Cosh, hyperbolic cosine, C-O-S-H for hyperbolic, is 1/2 e to the theta plus e to the minus theta. Now, in quantum mechanics, and therefore also in physical chemistry, these forms come up in wave functions, quantum mechanical wave functions a lot. And if you have an imaginary exponent, you're going to get oscillatory behavior out of this, a normal sine or a cosine. But if you have a real exponent, you get a damped pattern. It doesn't keep oscillating, it just sort of exponentially decays down to 0. Or asymptotically approaches 1 or whatnot. So, sinh and cosh there. Now, the hyperbolic tangent is sinh divided by cosh, hyperbolic sine over hyperbolic cosine. And it turns out when you divide these two, let's see, we can simplify this since each term has an e to the something times theta in the exponent. If we multiply numerator and denominator by e to the theta, okay, we're just multiplying by 1, cleverly disguised as a ratio of two exponentials. Then, in the first term, we've got e to the 2 theta minus e to the theta minus theta is e to the 0, which is 1, divided by, now we got e to the 2 theta again, plus e to the theta minus theta, which is 0, e to the 0 is 1, there. So the hyperbolic tangent of theta is e to the 2 theta minus 1 over e to the 2 theta plus 1. And what do we have right in here? And I should have turned it around. That's all right. We've got 1 minus e to the 2 something divided by 1 plus e to the 2 something. Well, that gives us, if I'm thinking this correctly, yeah. All right, so we just have an overall negative sign. This is negative times the hyperbolic tangent of mu b over kt. This chalk feels like plastic. It doesn't move right. Okay. Make sure that negative sign stands out there in front. So what we have now, we found that the energy of the whole system is equal to negative number of particles, number of dipoles, times mu b, mu being the magnetic dipole moment, which gives you the magnetic field strength of each one of the little particles in there, the dipoles, times b, the external field strength, times the hyperbolic tangent of mu b over kt. Now notice how kt always go together. I mean, it's units of energy when you multiply the temperature by Boltzmann's constant. Well, mu and b seem to hang around together in this problem as well. So it's not surprising to see the two of them. Okay. And that also means that mu b must have the units of energy because kt does, and they have to have the same, sorry, we have to take the trig function, the argument here has to be dimensionless units for it to work, and it is. Okay. Well, great. What does that get us? Well, we're going to do one more thing, and then I'm going to graph these, because the graphing is the really surprising thing. Let's see. I think I've got just a little more room here. One more thing I want us to find. We've got the energy, and uniquely to this problem, we also have that term, the magnetization. Capital M, for you add up the magnetic moments of all of these, positive and negative mu. We already found that the magnetization comes out to be equal to negative energy over B, the magnetic field. So since we've got that, which is a nice simple formula, we can just take U, negative U divided by B. That's great, we've got a B right here. And we've got a negative sign, so that cancels out. So we get the magnetization of a paramagnet is positive in mu times tanh mu B over KT. We've just used the result we just got for the total energy. Now, a hint, sort of a strategy, a tactic. When you see this kind of anti-symmetry here, it should, or symmetry for that matter, involving exponentials, it should make you look for trig functions using what are called the Euler relations. So if you see, 1 minus or exponential of this minus exponential of the same thing with a minus 1, or plus the exponential of the same thing with over a minus sign. Those Euler relations for the trigonometric functions always have those in them, and so you should look for those. Okay. One more thing to calculate, and then we'll get to graphing these, and that's the heat capacity. See if I can zoom in. Probably not. Okay. Notice I didn't find the heat capacity constant volume, which is what we had really derived before for a normal system of the gas. This thing doesn't really have a volume, the volume as a parameter in it. Obviously it's got to take up some space, but that doesn't come into the physics at all. What we're going to be interested in is heat capacity at constant, magnetic field will be useful. So we're going to hold, out of the variables we've got, we'll hold the number constant, number of dipoles, and the magnetic field, the external magnetic field strength, which in principle could vary. So we'll hold that constant in this case. So this is heat capacity at constant magnetic field. Okay, we've got our equation for the energy in terms of temperature. So, let's see, that was negative N mu B over, negative N mu B times hyperbolic tangent of mu B over KT. So if I take the derivative with respect to T, negative N mu B are constant and multiplied by the rest. So I can pull them outside the derivative. Now I'm going to take the derivative of the hyperbolic tangent with respect to T. With number and B constant. Okay. So you might ask yourself, what is the derivative of a hyperbolic tangent? Well, this one I had to look up in the derivative tables, honestly. You could easily, well, not difficultly. You could work it out from the Euler relations, because you can take the derivative of an exponential pretty easily. And it's a little bit of work here because you've got numerator and denominator and so on. But when you do it, you come up with the following. All right, so we wind up with a positive sign. We've got nk. Why did k come out? Because k was multiplied by the temperature, and we're taking derivative with respect to temperature. UV over KT, quantity squared, times 1 over hyperbolic cosine squared. So 1 over cos squared, or just cos to the negative 2 power. There. And if you want to write it as a fraction here, instead of putting cos to the minus 2, okay, there we go. Great. Now we've got the heat capacity, a constant magnetic field. So it tells us how much heat it takes for a rise in temperature. What are we going to do with these? Let's take a look. Let me see here. Oh, no, that's why I am. So let's see how entropy, temperature, magnetization, and heat capacity vary with energy or whatever else. Okay, so looking back at our equation for the entropy, let's see, if I can find my equation, I would see that the entropy depends on well, I had it in terms of n and n up. And while I didn't really rewrite it in terms of other things then, it was easier just to go on and take the derivative with respect to energy in order to get the temperature. And so I rewrote the derivative with respect to energy as a derivative with respect to n up. So I took a bit of a shortcut. But if you rewrite the entropy in terms of the energy, which you can do, several terms long, what you would find is that if you plot entropy, we'll do it as S over K. We'll divide out by Boltzmann's constant, so we get a dimensionless number. Then we can find that there's U over mu B appearing in the entropy equation. So if we look at varying energy per mu B, UB has units of energy, and so this is a dimensionless number. And it turns out that as we vary it from negative to positive n, where n is the number of dipoles, number of something is dimensionless as well, we get this curved shape like that out of it, where this does not go down perfectly straight at either end, but about like that there. Okay. So when we have it, when we have the energy being negative on this side here, let's see. We start off, if we have the energy be negative, now let's see, if energy is negative, that means that most of the dipoles are aligned with the magnetic field. If the field is pointing up, the dipoles, most of them are aligned with it as well. They're in the negative energy state, and if the total energy is negative, we're on this side over here. Negative energy, we'll look at the slope of entropy with respect to energy. At the lowest energy, you have a very steep slope. And I don't have any color chalk here, so I'll have to draw this. It's very steep here. Steep with a positive slope. As you increase the energy, it becomes more shallow, but still positive. When you get to an energy of 0, well, by the way, what does it mean to have an energy of 0? That's not the lowest energy state in this case. It's not like a gas. That means that you've got equal number of dipoles pointing up, low energy state, and pointing down, the high energy state. Okay, at that point, the slope of the entropy graph is 0. And as you keep increasing the energy, you get more of those dipoles to flip to anti-line from the field. You wind up with a shallow negative slope, and finally, at your maximum energy, you've got a steep negative slope. Great. So what? Well, since so what is, remember, one over temperature equals ds by du, which is the slope here. Okay. This means that at the lowest energy state, 1 over the slope is our temperature. We have a steep positive slope, which means we have a low positive temperature. As you increase the energy, you get a shallow slope, so 1 over that is a large number, a higher positive temperature, and when you get to 0 energy, your slope is 1 over 0, which is infinity. So I'm going to plot out the temperature here. In fact, for quantitative reasons to plot it, the book plots kT over mu b. But if b is being, let's see, it's actually a little more complex than that. It illustrates it well, but you've sometimes got to dig through these, kT over mu b to find out really what's going on. Anyway, we're plotting the temperature effectively here in units of K over mu b. Okay. And we're plotting it versus U over mu b, just as here. Okay, so at negative n, we've got a steep positive slope. One of that is a low positive temperature. And as you increase the energy while it's still negative, your slope shallows up so the temperature increases. And as you get to an energy of 0, your slope goes to 0, so 1 over 0 is infinity, and you asymptotically approach infinity, infinite temperature there. Here's the fun thing. What if you keep adding energy? Because you're still on the negative energy side of this. If you keep adding energy and you flip more, a majority of those dipoles to pointing against the magnetic field, now you have a shallow negative slope. So what's your temperature? Right? If you've got 1 over a small negative number, the temperature is a large negative number. And it's symmetrical, or, well, anti-symmetrical because of that slope. So it goes from negative infinity here, and then you finally go down to there. This is the weird part. You have negative temperatures when you have positive energy for the whole system. I should have put that our temperature one over temperature here, what we're actually plotting is K over 2 mu B times the natural log of n minus u over mu B divided by n plus u over mu B, which of course is related to the hyperbolic tangent. Log of that. Okay. Negative temperatures. And yet we're using the Kelvin scale. And what was the whole idea of the Kelvin temperature scale? That's right, there are no negative numbers. But we found some. Really what we should say is that the Kelvin temperature scale has it does have an absolute 0 for normal systems like gases and salts for that matter. So why is it we can get these negative temperatures here? This is the strangest behavior. And the negative temperatures actually is for the system with more energy in it than the positive temperatures have. So it's because we've got a maximum energy, and for that matter, a maximum entropy to it. And gases don't really, in principle, have that, or in practice have that. They can keep increasing their energy if they have a larger volume or higher temperature or whatever else like this. They kind of go together. Whereas this has an absolutely capped maximum energy. Once all of the dipoles are pointing against the magnetic field, that's all the energy you have. And your maximum entropy is when roughly equal numbers are pointing up as pointing down. But for a gas, as you keep pouring heat into it, its energy goes up, its temperature goes up, its entropy goes up. And here they're going in all different directions. Okay, 2 more things to graph. Magnetization and then the heat capacity. So magnetization let's see. in mu tanh of mu b over kt. Okay. Because magnetization is negative U over B, negative energy over magnetic field, then we're going to plot it in terms of, well, not U over mu B, but KT over mu B. It will be our variable, our independent variable. Despite the fact that we've got the formula written as in mu tanh of mu B over KT, so we're actually inverting this argument here. So it's, again, which way you want to plot these is not always immediately obvious. Okay, so if we plot magnetization over in mu, which is a convenient way to do it, you get that there, with making a discrete jump at this point here. And then finally, the heat capacity. We'll plot heat capacity over Nk. Let's see here. Our formula, recall, is Cb over Nk. I've already divided through by Nk here. Is mu b over kt quantity squared divided by cosh squared of mu b over kt. I think on the camera this last bit's going to be a bit hard to see. It's very small. Maybe I can zoom in some. Nope. Okay, so I'm saying it out loud. So if I plot this, Cb over Nk versus Kt over mu b, we wind up with a sharp rise from 0 up to a peak, a maximum heat capacity, and then a gradual tailing off as you increase the temperature. Really an unusual system. And again, it comes about the strange behavior of this, especially with the temperature, which defies everything we've been taught about temperature all the way from our introductory classes. Comes about because we have a maximum energy inherent in the system, with our entropy reaching its peak when the energy is 0. Okay, that's really got it there. This concludes our paramagnetism.